I'll just give you a brief. Can you roll?
Is it on?
Okay, so today we have Takashi Kurumaji from MIT. We'll be telling us about Skyrmions. And in the old days when I was young, I used to work on magnetic bubbles, which looked like hockey pucks that he would use as memory sites to move around. Skyrmions are a whole lot smaller than that. Looks like a twisted magnetic domain wall or something. You'll see pictures. But very interesting new sort of magnetic structure. He worked at the University of Tokyo and Kakura's group. Kakura runs both groups there and then a center out at Riken in Wako outside of Tokyo. And they both grow new quantum materials to house these kind of structures and then study how they work.
Thank you for introduction and thank you for coming to the QMD seminar. Good afternoon, everyone. My name is Takashi Kurumaji from Department of Physics of MIT. Today's result I'd like to talk about is not the work performed in MIT, but my former institution, Riken SEMS in Japan. This is about the Skyrmion lattice in a frustrated magnet. And let me start from the introduction of this talk of introducing the two key concepts to representing my result. This is a topology and a frustration. So the topology is a concept from the mathematics. It's providing the way to classifying the global quantity, classifying the object in terms of the global quantity, such as the number of holes. So donuts and Danish and pretzels has different number of holes, and you can classify it in terms of the different topological numbers. The same concept is very useful to understand the electronic property in solids. The remarkable example is the quantum Hall effect, which shows the quantization value of the Hall conductivity. It is integer number times the universal constant, regardless of the detail of the structures. So understanding this phenomena is possible by introducing the concept of topology, such as calculating the Chern number of band structures, which shows the quantized number 1 to 3 for each plateau state. So applying the magnetic field, you can tune the electronic state to switch the quantum number. It becomes a different topology of the electronic state. So the magnetic frustration is another concept to understand the magnetic property of the spin systems. This is a situation when not all the interactions can be stabilized by, satisfied by the magnetic interactions. So the simplest example can be obtained by this triangle bracket interacting the antiferromagnetically with each other for the spins on each side, and you cannot find a way to stabilize the spin moment on the third side. So this situation happens in many magnetic systems, and sometimes the system cannot find the way to form the magnetic ordered state down to the 0 temperature to become the spin liquid state. And in the case of the different lattice, such as the pyrocolor lattice, the three-dimensional network of the pyrocolor, so-called pyrocolor lattice, it becomes a spin ice. And the other case, the material finds a way to stabilize an exotic spin structure, such as the spiral spin structure. This is a rotation of the spin moment along certain direction in the lattice. So today's topic is about the blend of two concepts, the topology and the frustrations. So it's about the discovery of the new frustrated magnet, which finds a way to stabilize as an exotic spin structure characterized by the topology. It is Skyrmion. So let me show you the outline of this talk. It is composed of the 3 sections. First one is, let me introduce the Skyrmions. And actually, there are lots of study about the Skyrmions in magnets, which is stabilize the Skyrmion with different mechanisms from the frustrations. So the second part, I'd like to show you some theoretical ideas to stabilize the Skyrmion in the frustrated system, the different mechanism from the conventional Skyrmions. And I'd like to emphasize what is the difference coming up from the frustration mechanism. The third part is about the experimental result we obtained from the exploration of the new frustrated systems. So let me introduce the Skyrmions. Skyrmion is the topological spin vortex like this. So it has a spin moment downward at the core, the center of the Skyrmion, and it's going to the outside. The spin continuously rotates to the upward. So this spin structure cannot be destroyed by the continuous deformation of the spin moment, and it's characterized by the topological property. You can define the topological quantity of the Skyrmion by calculating the topological number, so-called Skyrmion number. This is the integral of the Skyrmion density, and you can find that this spin configuration is quantized into the -1. So it is corresponding to the number of how many times the spin moments wrap the sphere. It is thinking about the mapping of the spin configuration from the two-dimensional system to the on the surface of the block sphere. So it wraps the once for this spin configuration. This kind of topological spin soliton was first discovered in the chiral magnet. It is belonging to the B20 alloys composed of the transition metal and the non-magnetic silicon or germanium. The first material is a manganese silicide. The magnetic phase diagram is shown here, and you can see the small pocket region around the transition temperature, so-called A phase, and they identified the presence of the Skyrmion lattice state in this A phase region by the neutron diffraction technique. So the real space image of the Skyrmions are also demonstrated by using the Lorentz transition electron microscopy technique, as shown here. So each Skyrmions can be seen by the rainbow color wheel, and the spin configuration is as shown here. So it's forming the triangulars in the real space. So as well as the diffraction technique and the real space observation technique, you can detect the topological property of the Skyrmion by measuring the Hall resistivity. This is so-called the topological Hall effect. So the Skyrmions, let's thinking about the motion of the conduction electrons on the background of the Skyrmion spin configurations. So electron has each spins, and thinking about the strong Hund coupling between the local moment with the electron spin and propagating on through the Skyrmions, the spin moment will rotate following the local spin configuration. So in this case, the conduction electron feels the additional vector potential A. It is related with Berry connection of the electronic wave functions, and it is corresponding to the fictitious magnetic field by taking the rotation of the vector potentials. And so the motion of the electrons on through the Skyrmion feels a fictitious magnetic field, and this propagation direction will be deflected on to the perpendicular direction of the propagation directions. So this is proportional to the Skyrmion density and can be detected. So the presence of the Skyrmion can be detected by the measurement of the Hall resistivity. So the topological Hall effect has been observed in first in manganese silicide under the pressure as well as the ambient pressure condition. So as you can see from this state.
I had a question because you were talking about Berry curvature and
Yeah.
things that look like a magnetic field but aren't actually a magnetic field, or what?
It's a fictitious magnetic field. So electron feels the presence of the additional Berry curvature moving on the Skyrmion. the effect of this Berry curvature is the same as the magnetic field in the real world. So the electron will propagate feeling the presence of the magnetic field, and the same dynamics will happen as in the case of the presence of the magnetic field.
But it isn't actually a magnetic field.
It isn't actually the magnetic field, but for the electron, it's almost the same with the magnetic field.
It changes. It's in the Hamiltonian, you get P minus E over CK.
Yeah. So it is.
Like the A and
It is an effective magnetic field, so you can get by the gauge transformation from the real spin Hamiltonian to the spin Hamiltonian for an electron.
Okay.
Yeah. So the real the resistivity measurement, you can detect the topological Hall resistivity, and in addition to the background Hall resistivity, you can identify some additional feature, and exclusively in the A phase region is identified as a topological Hall effect due to the Skyrmion. Under the pressure, the shrinkage of the Skyrmion length scale happens. It enhances the emergent magnetic field, so the Hall anomaly is more clear in the pressure. So the microscopic mechanism to stabilize the Skyrmion can be understood by the presence of the Jaroszynski-Moriya interaction, which is activated by the inversion symmetry breaking. So in addition to the ferromagnetic interactions, the inversion central symmetry breaking system hosts Jaroszynski-Moriya interaction, which favors a twisted spin configuration. So in the case of the one-dimensional chain without the inversion symmetry, with the dm vectors, pseudo vectors along the chain directions, the electron will be twisted to form the spiral structures. So the generalization of this scenario into the two-dimensional system is obtained by taking the continuous limit of the spin structures. So because of the long wavelengths of the modulation. So in this case, the Jaroszynski-Moriya interaction has this term proportional to the linear term of in terms of the spatial derivative, and it favors the twisting of the spin in every direction in the two-dimensional space to favor the Skyrmions. So the important point is that the magnetic modulation wavelengths is determined by the ratio of the exchange interaction and the Jaroszynski-Moriya interaction. And the DM interaction is coming from the relativistic effect. It's 100 times smaller than the exchange interactions. So it determines the typical size of the Skyrmion to be the 10 to the 100 nanometers. So discovery of the Skyrmion lattice formation in chiral magnets accelerated the study of the non-central symmetric magnets to lead the discovery of the various non-central symmetric magnets to host the Skyrmions. As well as the chiral magnets, there are many different types of non-central symmetric magnets, polar magnets, or the interface of the magnetic thin film. It also breaks the mirror inversion symmetry and has polarity perpendicular to the plane. It also favors the twisted spin configurations to stabilize the Skyrmion. And D2D magnet is another type of non-central symmetry, also can host the Skyrmion. So this is a minor detail, but different type of non-central symmetry can host the different type of Jaroszynski-Moriya interactions to stabilize a different form of Skyrmion. So in the case of the chiral magnets, this type of Skyrmion is stabilized, called a block-type Skyrmion. By taking a cross-section along here, the spin configuration can be viewed as the proper screw-type spin configuration. In the polar magnet, this type of nail-type Skyrmion is stabilized. It is a cross-section of the spin configuration is a form of a cycloidal type spin configuration. So D2D magnet has a different type of Skyrmion stabilized from the block or nail-type Skyrmion. This is called the anti-vortex type Skyrmion. And taking the cross-section, it is can be seen as a mixture of the cycloidal and proper screw structures. So important point is that the anti-vortex type Skyrmion cannot be continuously deformed to the block type or nail type Skyrmions, so can be identified as a different type of the topology.
The block type Skyrmion, topologically, you've got sort of a spiral of the spin going around in the middle.
So block type Skyrmion and nail type Skyrmion have the same topological number. So you can continuously deform the nail type Skyrmion to the block type Skyrmion, actually, by rotating this intermediate spin configuration, rotating 90 degrees. This is allowed to deform the nail type to the block type Skyrmion. So these two types of Skyrmion has the same topological number. But the anti-vortex type is different, opposite sign of the topological number. Okay, so the study about the Skyrmion stabilization in non-central symmetric magnets is well established, and design principle has already been known. As a matter of fact, I could also find new Skyrmion hosting materials activated by the Jaroszewski-Morier interactions. So the design principle is very simple. Brings the non-central symmetric magnets and carefully look at the phase diagram around the transition temperature. So brings the polar magnet, it breaks the mirror symmetry, and measuring the susceptibility very carefully, and identifies the very small pocket region in a low field region as an A phase, and perform the neutron diffraction. So we identified the characteristic sand pattern for the lattice formation of the Skyrmions. It is also confirmed by the polarized neutron scattering to be the nail type Skyrmion. So the finding out the Skyrmion is in a non-central symmetric magnet is relatively easy. So then, how about the magnetic frustration? And I'd like to explain what's the difference of the frustration mechanisms to stabilize the Skyrmion, and what kind of different physical property coming out from this mechanism. So magnetic frustration can support the spiral structure as well as the DM interactions. Can be understood by the simple model with competing interaction J1 and J2 on the one-dimensional spin chain. So in the case of the antiferromagnetic J2 interactions competing with J1, it cannot satisfy all the magnetic interactions, and the spin system finds the stable spin structures to be the spiral structures as shown here. So important point is the magnetic modulation wavelength, lambda, can be expressed by the formula of the exchange interactions, which is the spin doesn't have any parameter for the spin-orbit interactions. So several nanometer of the modulation wavelength is possible. So two-dimensional generalization into the two-dimensional system is straightforward. So as you closely look at the spin configuration of a Skyrmion, you can see that in some direction it has the spiral configuration as shown here. And due to the threefold rotational symmetry of the Skyrmion lattice, there are a different type of, there are also the spiral configuration for different axes 120 degrees with each other. As a matter of fact, mathematically, you can express the spin configuration of the Skyrmion by the superposition of the three equivalent spiral structures. So this is a key point to understand the stability of the Skyrmion due to magnetic frustration. So this is a Hamiltonian for the two-dimensional system, and let's think about, for example, the case of the triangular lattice, which has the competing interactions J1 and J2. But the interactions are around the AB plane. So in this case, you can understand the stable spin configuration by taking the Fourier transformation of the interaction parameters J. So it is a function of Q, and calculating the landscape of the JQ, you can get this result, and you can see that there are 6 different positions forming the local minimum of the JQ. So it determines the stable Q vectors of the modulated state in this frustrated system. So this means that the 3 different Q vectors are degenerate and have the same energy for 3 magnetic modulations. So this supports the formation of the superposition, the spin structure for the superposition of the 3 Q vectors, which eventually becomes the Skyrmions. So So important point of the difference between the TM-based Skyrmion and the frustration-based Skyrmion is the magnetic modulation wavelengths. Because of the absence of the spin-orbit coupling in the formation of the modulated state, the magnetic frustration mechanism is possible to have the several nanometer side of the Skyrmion. So as you can see from the formula for the emergent magnetic field, in the frustrated system, you can have a chance to encounter the enhanced topological Hall effect due to the miniaturization of the Skyrmion size.
So if I wanted to design a material that would show Skyrmions, what I get from what you're saying is that you want to put in something that will twist if I'm moving in one direction. That will put a twist, a corkscrew kind of, forget the corkscrew, but a twist in this direction of the electron spin. And then when you try to stack this in different directions, it will put a twist in the main walls.
Yeah, that's true.
That's essential. That's the cause of increase.
So there are two different types of the Skyrmions, which has a different helicity, but it is a kind of a handedness of the spiral structures. But the handedness doesn't affect the sign of the topological Hall effect. Both of them have the same topology. So the topology is the difference between the handedness, and doesn't affect the magnitude of the topological Hall effect, even in the case of the central symmetric frustrated system.
But no twist, no Skyrmion?
No twist, and no Skyrmion, I think, yeah. So I'd like to briefly review the theoretical papers which provide the ideas to stabilize the Skyrmion state, which is enforcing the previous naive ideas. So one of the theories is about the calculation of the Monte Carlo method using the spin Hamiltonian with the isotropic interactions as well as the Zeeman interactions. In this case, the theory predicts the presence of the Skyrmion in the intermediate temperature region. So it suggests that the thermal fluctuations support the presence of the Skyrmions compared with the simple helimagnetic state. So the other theory predicts the different mechanisms, which is adding the uniaxial anisotropy term. And this theory predicts the presence of the Skyrmion even in the zero temperature. So this is a calculation under the magnetic field with some parameter values. They find the stabilization of the Skyrmion phase in this area. So the uniaxial anisotropy is also the important parameter to stabilize the Skyrmion. So the third theory provides an interesting viewpoint for the stabilization of the Skyrmion in the metallic system. So they calculate the central symmetric RKKY-based intermetallic systems. So they start from the Kondo lattice models and deduce the effective Hamiltonian, which is composed of the RKKY type usual interaction, as well as the biquadratic term, which is coming from the fourth order perturbation of the RKKY interactions. And they calculate the system which has the Fermi surface instability due to the nesting of the Fermi surface, and calculate the effective Hamiltonian and find the stable spin structure contains the Skyrmion lattice state under the magnetic field. So interesting point of this theory that they also predict the emergence of the different type of spin texture, which has a different topological number than the Skyrmion lattice state. So its theory provides us some expectation to encounter the different exotic type of the spin texture in the RKKY-based intermetallic systems. Okay, so based on these theoretical ideas, I'd like to add some different aspects from the viewpoint of the experimentalist to stabilize the Skyrmion lattice state in the central symmetric systems. Because I'd like to design the new Skyrmion hosting material due to the magnetic frustrations. So I'd like to show some 3 requirements to stabilize the Skyrmion state. One is bringing the geometrically frustrated lattices due to for the modulated spin state. So triangular lattice, honeycomb lattice, and many frustrated system can be the possible candidate. And the second design principle is ferromagnetic interlayer coupling. Because of the 3D image of the Skyrmion, you can see that there is a Skyrmion tube from the top layer to the bottom layer. It has the same configuration of spin going through the sample. So it needs the ferromagnetic interlayer interaction in the system. Unfortunately, in the metals, this kind of interlayer ferromagnetic coupling many times happens. So it's promising for encountering the Skyrmions. So the third design.
But is it necessary to have atomic layers in order to have the Skyrmions, or how thick could your film be before it would?
So I'm looking for the Skyrmion state in the bulk sample. So in the thin film, it can stabilize the Skyrmion state with a different mechanism, the DM mechanisms, because of the inversion symmetry of the thin film. But in the case of the bulk sample with central symmetry, there's no DM interactions. The frustration mechanism can be the driving force to stabilize the Skyrmion. So the third mechanism, a third requirement for the candidate compound must be the weak anisotropy because of the spin configuration of the Skyrmion is a non-coplanar type order. So Heisenberg type spin in the gadolinium or europium manganese iron can be the possible promising candidate. And this result is today's interest is about the first example of the Skyrmion lattice formation in the triangular lattice state. So let me introduce the target compound. It is a rare earth-based compound contains a palladium and a silicon. Crystal structure is like this. The stacking of the triangular lattice of the rare earth sandwiching the non-magnetic and palladium and silicon atoms. An interesting point of these families is that many previous results reveal that the presence of the modulation of the magnetic ordering, suggesting the presence of the magnetic frustration, such as chromium 1/7, the erbium, and dysprosium, and as well as the terbium. In the terbium, they also perform the RPS measurement to reveal the nesting of the film surface to lead the stabilization of the modulated spin state. But there has not been the gadolinium compound. That's why I chose the gadolinium compound as a target compound. So it's satisfying the three requirements of the target compound, and as well as the also there are the previous results showing the interesting properties. So it is reported to have the metamagnetic transition as a magnetic field, suggesting the frustration leads to the degenerate spin configuration. And observed the large magnetoresistance. It also supportive to expect the presence of the strong interaction between the conduction electron and the localized spin. So you can expect the emergent electromagnetic property from the system. So we grew the single crystals using a floating method and obtained the beautiful single crystals and reproduced the magnetic properties as shown here. And we also checked the crystallographic property using the TEM technique and X-ray diffractions and found the superlattice structures in terms of the ordering of the palladium and the silicon. This has also already been reported in the previous results. It is in terms of the expansion of the unit cell along the C-axis and the AB plane axis. In spite of this complexity of the crystal structures, it still holds the inversion symmetry, excluding the Jaroszynski-Mobius interaction as a dominant mechanism to stabilize the modulated state. So the magnetic frustration can be the mechanism to stabilize the modulated state. So let me avoid the complexity and express the magnet unit cell, crystallographic unit cell with original simple aluminum B2 type structures. And I measured the magnetization under the application of the magnetic field along the C and A axis and reproduced the two-step metamagnetic transition as shown here, only when the H is parallel to the C axis. So measuring the susceptibility, we also identified the phase boundary by the peak of the susceptibility and obtained the anisotropic phase diagram manifest the presence of the intermediate phase, so-called A phase, for the H parallel to the C-axis. So in order to confirm the topological property of the A phase, we measured the Hall resistivity and observed the large enhancement of the Hall resistivity accompanied with positive magnetic resistance. So it's quite similar with the observation in the manganese silicide suggesting the presence of the topological Hall effect. So it also has a positive magnetic resistance in the A phase regions as well as the hump in the Hall resistivity. And we also extend the measurement to the high temperature and high magnetic field to reveal that this Hall anomaly disappears above the transition temperature, and the Hall resistivity for high field is almost linear, suggesting the presence of only the normal Hall component, as well as some minor anomalous Hall effect. So only the measurement of the Hall resistivity is not enough to identify the topological Hall effect. We have to decompose each component of the Hall resistivity. So what we did is comparing the Hall resistivity with the magnetization. So in general, the Hall conductivity, Hall resistivity is composed of three different terms: the Lorentz force-related normal Hall term, and a conventional anomalous Hall effect proportional to the magnetization, and the topological Hall effect. So looking at the magnetization at 14 Tesla, it's almost saturate, and we can safely say that the magnetic structure in this region doesn't have the topological property. So we can fit the Hall resistivity with the first two terms in this area. So that's the result we obtained, and we successfully simulate the background for the Hall resistivity, and subtracting this background, we obtain the topological Hall signal, which is has the magnitude only around the A phase regions. So we took the data and performed the analysis for different temperature and identified that the all temperature region we successfully performed the analysis, and this is a color plot of the whole decomposed Hall resistivity. Identify that it is exclusively exists only around the A phase region.
So is it right to say that the big Hall effect is coming out of the Berry phase?
Yeah, that's true. That's true. Yeah, yeah.
And it looks like it's a large magnetic field that makes that texture, and then bends the electrons.
Yeah, that's correct. That's correct. Yeah. So this is the temperature dependence of the maximum value of the Hall resistivity. It has maximum value at lowest temperature, and estimating the effective magnetic field by dividing the Hall constant, it's corresponding to 39 Tesla, 10 times larger than that observed in the manganese silicide. Right. So it's clearly suggesting the presence of the large emergent magnetic field. So we also confirmed the two-dimensional nature of the Skyrmion by rotating the magnetic field. The Skyrmion is stable when the H is close to the C-axis, but rotating the magnetic field towards the AB plane, it's destabilized because of the one of the Q vector will be selected to be the non-topological magnetic structure. So we observed that the switching of the topological Hall signal by rotating the magnetic field clearly showing the topological phase transition by the rotation of the magnetic field. So this is a phase diagram of the topological Hall signal, as well as the magnetic phase diagram determined by the susceptibility. So only the field is lower than the 60 degrees, the A phase region appears suggesting the stability of the two-dimensional spin texture only in the magnetic field around the C-axis. Okay.
Another simple question. When you're making these structures, can you think about the Skyrmion as being an entity that's happy by itself, so that you can see one of them and nothing else, and that they move around and form a gas? Or does it always look like a muffin tin where they're all stuck together?
Yeah, that's an interesting question. So we still don't know the answer for these materials, but in the non-centrosymmetric magnets, exactly the same thing happens. So the skyrmion will be isolated and moving around by the magnetic the flowing current. But this is an ongoing project for these materials. The isolated skyrmion exists or not is an open question. Okay, so in order to determine the spin structure of these materials, we performed the Lorentz TEM observation of the spin structures. So this is a powerful technique to visualize the real space image of a spin texture in the conventional non-centrosymmetric skyrmion hosting materials or the magnetic bubbles. But in the case of the frustration-based skyrmion compound, because of the short wavelengths of the spin modulation, the obtained data is shown here. It's not so clear what's going on inside, but taking the Fourier transformation, we clearly identify the presence of the hexagonal spot, suggesting some implying the presence of the skyrmion lattice state. So taking the inverse Fourier transformation, we by masking of this peak and picking up the peaks, we partially reconstruct the spin configuration image of this material. But still, it's a little bit challenging technique and ongoing project to observe the real space image of the skyrmion state in this system. So we took the different approach to realize, to identify the spin structure in the system. We performed the resonant X-ray scattering. This is making use of the excitation of the electrons on the gadolinium moment, picking up the information of the gadolinium spin directory. So this is the collaborators, and the measurement was performed at Photon Factory at Keck in Japan. So we successfully observed the resonant peak for corresponding to the gadolinium resonance and identified the satellite peaks demonstrating the modulation of the spin structures. So this is a peak around the 220 black spot and suggesting the in-plane magnetic modulations. So we took the data at various temperatures and confirmed the signal disappears when the temperature is above the magnetic transition temperature. So this is magnetic scattering. And the observed magnetic modulation is around 2.5 nanometers, 7 times shorter than the manganese silicide. So it's also consistent with a giant emergent magnetic field in this system. So we also performed the measurement under the magnetic field and also confirmed the presence of the in-plane modulation in the A-phase region. So this is a field dependence of the Q vectors, and we confirmed that the presence of the modulation in the A-phase region is consistent with the presence of the modulated spin structure in the A-phase. Okay, so this is a bit detail, but we also confirmed the spin configuration. As I told you, there are 3 different types of skyrmions, block, anneal, and antivortex, and we would like to determine the spin texture by making use of the sensitivity of the spin in terms of the polarization of the resonant X-ray. So the resonant X-ray has a magnetic scattering term as shown here. So using this relationship, you can determine the spin configuration of the skyrmions. So in the case of the polarization scattering from the pi to pi, it captures the information of the magnetic modulation along the z-axis. But in the case of the pi to sigma polarization, it can capture the in-plane magnetic modulation. So comparing the intensity for the different satellite peaks, you can determine the magnetic structures. So this is the result for the pi-pi scattering, as it's picking up the mg component of a spin modulation, almost equivalent for each q vectors, consistent with the equivalent triple superposition of the 3 modulated spin structures. But in contrast to that, we observed the strong Q dependence of the intensity for the pi sigma scattering. So this is because of the in-plane magnetic modulation for each Q vectors have a different orientation, and it has a sensitivity to the vectors spanned by the polarizations. So this is consistent with the formation of the block-type Skyrmions, as shown here. And we also confirmed this conclusion by taking the same measurement on different Bragg spots, as well as the 220. So we rotate the diffractometer to approach to the different Bragg spots and measured the Q dependence. So each of them has a different Q dependence, but all of them is well explained by the proper screw spin structure model consistent with the formation of the block-type Skyrmion. Okay, so getting the information of the spin texture, we can estimate the emergent magnetic field. So this is a list of the Skyrmion materials comparing the wavelengths and topological Hall signal. So as you can see, the gadolinium compound has shortest magnetic modulations, and topological Hall signal is the largest. So you can estimate the emergent magnetic field by using the magnetic modulation wavelengths. It is estimated to be 570 Tesla, and compared with estimated value from the topological Hall effect, it's 10 times smaller than this value. This is because the spin is not fully polarized. So the spin conduction electron spin up and down feels the opposite value of the topological Hall signal. So it's cancelled out, but the uncancelled component is observed as a topological Hall effect. So the polarization factor is estimated to be the 0.07, which is almost 1 order of magnitude smaller than that for the manganese silicide. This is because of the difference of the molecular field of the localized moment to the conduction electrons through the F decoupling or the S decoupling in the manganese silicide. But in spite of this smallness of the polarization factor, the topological Hall signal is still large, and it's manifests that the magnetic frustration is very supportive to shrink the Skyrmion size to enhance the emergent magnetic field. So we also performed the detailed resonant X-ray scattering to identify the spin structure of the other magnetic phases, higher and lower magnetic field compared with A phase. So IC1, IC2 state, for example, doesn't have the pi-pi scattering to be identified a non-topological spin texture as shown here. And in contrast to the IC2 state, IC1 state seems have some interesting spin textures because it has the suggestive experimental evidence suggesting the triple Q state. So let me skip the detail, but it's still under controversy, but we propose that the IC1 state can support the magnetic spin textures described by the triangular lattice of the meron and antimeron, different topological, different topology from the Skyrmions. So it has the different, each layer areas has a different topological number, 1/2 and minus 1/2. It cancels the topological number in the global area to be a topological number 0, and it is different from the Skyrmion lattice state. And calculating the emergent magnetic field, as you can see that it's cancelled out with each other to cancelling the topological Hall effect. This is consistent with the absence of the topological Hall effect in the 0 field. But we would like to emphasize that this structure can explain the detailed feature of the topological Hall signal. So as you closely look at the topological Hall data around the 0 field region, it starts from 0, but linearly increases by the magnetic field before entering to the A phase region, the topological spin texture. So it has some topological Hall effect even in the IC1 state. It is inconsistent with the presence of the normal helical magnetic structures. So but this triple Q state can explain because of the topological Hall effect because of the finite vorticity in the core of the spin texture. Okay, so this is a kind of a one-slide summary of this result. So bringing the material with the magnetic frustrations, you can tune the magnetic structures, and by application of the magnetic field, you control the topology of the spin structures in the system, and which enhances the emergent magnetic field coming from the interaction between the conduction electron and the localized spin. So we would like to emphasize that this works. This demonstrates the powerful result of this design principle of the Skyrmion systems, and we push the project forward to search for the new Skyrmion systems using this design principles. And actually, we found the other Skyrmion hosting system in the different type of the lattice with the magnetic frustrations. So this is a gadolinium ruthenium aluminum. It hosts the breathing type of the Kagome lattice. So it has a different bond length. They are frustrated with each other to support the modulated spin structures. And we confirm the presence of the spin texture consistent with three triangular lattice of the Skyrmion and observed the topological Hall effect. And we identified in this material also host the Skyrmion lattice state in the magnetic field, suggesting the strong design principle of the I suggested. So okay, this is a summary of my talk. So the magnetic frustrated system is a relatively simple crystal structure, bringing just the triangular lattice or a honeycomb or something, and you can achieve the magnetic frustration. But even these simple structures, you can realize a very complicated spin structure like a Skyrmion, which has a topology, and this enables to have the giant topological Hall effect due to the emergent magnetic field. So this is the main message. The magnetic frustration can be used as a knob to tune the topology in the condensed matter. So let me acknowledge the collaborators, and thank you for your attention.